Hi, I am Professor Mrigank from Department of Electronics and Electrical Communication Engineering at IIT Kharagpur. It gives me great pleasure to launch this course at the NPTEL platform titled Analog Mixed Signal Circuit Design through SPICE Simulations. Analog circuit design is a very intensive, conceptually as well as practically very intensive course in the UG as well as PG curriculum, and it attracts a lot of undergraduate as well as postgraduate students because of its stimulating nature. Along with that, of course, it has very strong link with the current industry trends and lots of practical applications related to discrete circuit design as well as integrated circuit designs. The material covered in the analog electronics courses at undergraduate as well as postgraduate level, they generally deal with analysis of transistor level circuits, maybe DC analysis, AC analysis, frequency response, biasing strategies, and the basic strategies used for building the essential components of analog circuits and analyzing them thoroughly. All that concept involved happens to be pretty intensive. It takes a lot of time and practice to grasp all that concept, even for the smartest students. And even at the end of one full semester, it is difficult to guarantee that students majority of the class is able to assimilate all the concepts covered in such an intensive course. However, if students are given a feel of applying those concepts learned in a theory class in a practical example, the learning experience can be much more enriched. So that is the purpose of this course, where I am trying to offer a combination of theory as well as very rich practical design examples, employing those very fundamental concepts taught in the theory modules. The modules covered in the theory will be very much linked with a standard undergraduate course on analog electronics, where we will be refreshing some of the essential concepts at circuit level, starting from transistor operation, DC biasing, small signal analysis, frequency response, and some additional concepts like noise and so on. And along with that, each of these concepts will try to demonstrate using simulations. So this is supposed to be the initial phase of the course, where the fundamental concepts are going to be demonstrated using simulations. So it will be refreshing the materials covered in any undergraduate analog circuit course. Beyond that, the target of this course is to apply all those basic concepts, apply all those essential circuitry that we learn as a part of our regular courses into building something practical, into building a design which is linked to, say, current application trends. Towards that end, we are picking up a analog signal acquisition chain, which may be suitable for, say, sensor signal acquisition, essentially a biomedical signal acquisition system. There we will be looking at the different blocks, their functionalities, trying to arrive at their specifications starting from the application definition. So at the highest level, we have the application at hand for which we are trying to build our circuits, for which we are trying to apply our learnings and coming up with the design solutions. For that, first of all, we need to have the highest level system specification, that what are the signal characteristics we are trying to process, what kind of functionality we need to incorporate in order to achieve a certain functionality or a certain process data which goes into the digital domain for further processing. So that needs high level system definition, and from there we need to define what are the functional units, like the very front end amplifier which is supposed to interface with an external sensor and acquire the data. What are the characteristics of that front end amplifier? How does it interface with the sensor? How do we take care that the sensor interface is reliable enough and it is meeting the specifications? Likewise, in the pre-processing, analog pre-processing stage, we have so many different blocks which need to amplify the signal, filter the signal, remove the non-agilities like the baseline fluctuation, for example, or they may have severe constraint in terms of the noise level that the circuits can add. Apart from that, they have to meet several constraints in terms of, say, noise, linearity, bandwidth. So, from the highest level specification of the system, we gradually come down to block level specification and try to see what are the limitations or what are the challenges related to those blocks, and from there we derive the specifications of those blocks and then go to the circuit level design of those individual blocks. So, that helps us in linking the circuit design of those blocks with the highest level application or system definition, and that link is very important in order to appreciate the utility of whatever we learn in an analog circuit course. So, we will be looking at a comprehensive design example where, starting from the very front end of the sensor data acquisition, we have the analog signal acquisition chain, amplifiers, filters, going all the way to an ADC, and we will be looking into the block level specification design, and along with that going down to the deepest level, transistor level implementation of these individual blocks, meeting these specifications that we arrived at the highest level. If we look at the theoretical part of it, of course in the course we will have enough discussion on the basic theory component, which will help the attendants revise or review the content that has already been probably covered in their earlier courses on analog circuits. But along with that, the theory will always be linked with the simulation or design strategies. So, for example, when you are talking about frequency response or stability analysis, the way we do it in a theoretical calculation or a theoretical module is slightly different from what we have to do in the simulation, because in simulation we have some more things that we need to take care of. We need to be sure how to carry out those analysis in simulation. Doing something numerically is very different from doing the same analysis in actual simulations. There are certain settings that you need to take care of at the circuit level, so that those analyses are coming correctly. So, having the information about how to run the simulation at a transistor level and how to be able to implement or verify whatever we are learning in the basic theory is going to be important, and that is something we are going to address in the initial part of the course as well. So, whatever basic concepts we review, like the stability analysis, frequency response, feedback amplifier configurations, etc., along with that noise, their corresponding simulation strategy will also be discussed, and we will try to see how all those concepts we can verify using transistor level simulations. Now, when we come towards specifications and the block level specification and implementation of those blocks using transistor level circuits, once again there is a big gap between what we can expect in ideal simulations with ideal transistors and what happens in the real world. If you are trying to design a circuit using practical transistors, either a discrete component device or integrated circuits, there once again a lot of non-idealities of the transistors, of the devices or the components come into picture, and therefore it is very important that we are aware of those non-idealities, so that whatever designs we are building, that is robust enough, that is going to work under practical conditions. Therefore, we will be discussing all those intricacies, all those non-idealities that we need to address, so that we can have a better taste of what are the practical design challenges that can come into picture when we consider a comprehensive design example or design of different blocks for that particular application. Likewise, in the simulation module, once again we will be trying to address those non-idealities and try to make sure that whatever designs we are trying to build, they are comprehensive enough, and accordingly we will be looking at the different blocks and the block level interfacing and their issues. Along with that, transistor level design issues and non-idealities will be addressed thoroughly for each and every module. Now, in this course we are going to stick to CMOS platform. Of course, in an undergrad course we have good amount of emphasis paid to BJT circuits as well, but CMOS is the technology of the day, and for integrated circuit design especially, that is the key technology. Therefore, in this course which is more geared towards or more inclined towards integrated circuit design, we will be focusing on CMOS technology will be focusing on circuits built with MOSFETs or not. Along with that, we'll also try to distinguish the two kinds of designs that we can teach. One is the breadboard level design, where you can be using discrete transistors or components to build your circuits, where you have more choices in terms of component values, etc. And the other case where you have integrated circuit design, where the component choices and values are a lot more constrained, and there are additional design issues or constraints or limitations that come into picture when we talk about integrated circuit design or a chip design. So throughout the course, I will of course try to distinguish between these two domains. Whenever we are doing a simulation, I will try to clearly distinguish that what is possible in an integrated circuit environment, what is possible in a breadboard environment, so that the distinction is clear enough. So today, when we are in the age of data driven technology, where we have plethora of electronic devices coming up, which has been facilitated by the powerful CMOS technology, by the unprecedented scaling of CMOS technology, we have acquired immense computing power in the digital domain. And people are talking about devices which can be all pervasive, which can acquire a lot of data from different sources from all around, and they can channel that data to the powerful computing machinery, maybe local computing or maybe cloud computing, and through that humongous amount of data we can benefit, we can derive benefit for a lot of different applications. But so as this digital computing engine has expanded, of course the corresponding supporting envelope, that is the analog part, has also equally expanded, and the design challenges associated with that expanding analog envelope has also got enhanced. So today we are looking at more and more system level design challenges, application level design challenges. So it's important that whatever the students study as a part of a regular circuit course, whatever concepts they learn regarding individual circuits and components, they are able to link it with an application and look at the whole picture in totality. And that is one of the main purpose of this course. Starting from the scratch, when we are looking at individual circuits, components, we gradually build up and come to an entire system where the individual modules are linked together while addressing all the non-idealities, while addressing all the integrate design issues with individual blocks. We are able to arrive at a complete application. We are able to give a solution for a complete application. And I'm sure that this comprehensive example is going to be very interesting for the students, and it's going to be very helpful in stimulating their interest towards this subject, and also it can be equally interesting, it can be equally helpful for teachers who want to utilize this study material, the simulation modules, etc., covered in this course in their classes. So I hope this will be a good service to the students who are interested in this field, and also our teachers who may like to benefit from the simulation modules or the examples covered, so that they can also utilize this in their course. I have successfully employed these strategies, these simulation modules in our courses over here at IIT Kharagpur, and we have seen that it has been very effective, very helpful in stimulating interest among students. We have a lot of students showing good interest and doing good work, participating in more rigorous design assignments and modules after going through these kind of examples. So I am pretty sure that after attending this course, students will have more deeper insight, and they will benefit a lot from the theory as well as simulation modules. Not only the freshers, not only the undergrad students, but even graduate students in their master's level studies and PhD students in their early phases of studies, they may find this course useful, and they may be able to brush up the concepts related to analog circuit design, and get aware of some of the interesting issues related to simulation, and also issues related to practical non-idealities and the design issues related to a particular system. So it's a comprehensive example, starting from scratch, starting from the very fundamentals, transistors, circuits, going all the way to blocks, systems, and covering the entire example in totality. So I look forward to having interaction with all of you, and I hope I will see you in the course, and we'll all together enjoy this process of learning analog circuit through SPICE simulation. Thank you very much.